So lowering of vapor pressure is our one of the important colligative property, you can say. And we already gone through about colligative properties, right? Okay. So I'm just going to write first what is vapor pressure is. So I'm writing vapor pressure. Vapor pressure. Okay. But before vapor pressure, let me write about the equilibrium. What is equilibrium is? Okay, so I'm writing equilibrium over here. We'll do. Okay, what is equilibrium? When or at a constant temperature, beta, it always possible at a constant temperature only. That's why we had to write here at a constant temperature. So I'm writing here at a constant temperature. Constant temperature. At a constant temperature. Someone is in waiting room. Wait a second. Okay. At a constant temperature, when the rate of evaporation okay, of when the rate of evaporation or not of becomes equals to the rate of condensation. The rate of condensation of any volatile liquid is called as equilibrium. Understood everyone what is equilibrium is? Everyone keep replying, beta.
Yes, sir.
Okay, so this is called as equilibrium. Okay. Now we have to understand vapor pressure now, because vapor pressure is depend on equilibrium only. So that's why we have wrote first equilibrium. Okay, now I am going to write vapor pressure. Okay, so the pressure applied by vapors of vapors. Why someone is waiting, like coming waiting room again and again? Aditi Chaubule. What's wrong with her? I don't know. Okay. The pressure applied by vapors on the surface of, again someone is in waiting room. Devish. Okay. On the surface of liquid. On the surface of liquid at equilibrium. Is called as vapor pressure. It's called as vapor pressure. Understood what is vapor pressure is? Now we have to write about lowering of vapor pressure. Okay. So let vapor pressure of, I'm writing here vapor pressure of vapor pressure of pure liquid, or you can write solvent also. Okay, is represented by, it is P0 beta, P0. Okay, or you can write P10 also, will also do. Okay, P10. Understood? Okay, now lowering of vapor pressure. Lowering of vapor pressure. Okay, see, when lowering of vapor pressure takes place, yesterday we discussed, in last class we discussed, when any non-volatile solute is added or dissolved in volatile solvent, then it is lowered, right, everyone? Because number of particle of the surface decreases, okay, number of particle on the surface of solvent or volatile solvent decreases, that's why the rate of evaporation decreases. Is it everyone that we discussed in last class only, right? Do reply.
Yes, sir.
Yes. So I'm writing conditional, it is conditional one. So I'm writing condition beta. Okay. So I'm writing first condition. When any non-volatile when any non-volatile solute dissolve in volatile solvent, when any non-volatile solute dissolve in volatile solvent, then particles of volatile, non-volatile solute. Wait, let me erase that. Okay, particles of non-volatile solute distributed uniformly throughout the solution. Right, everyone? Out of which some of the particle acquires space on surface also, right, due to which number of particles of volatile solvent decreases, right? Is it everyone? Number of particle of the volatile solvent will decreases on the surface, na? Keep replying. Yes, on the surface. So what is it going to lead? It will decrease the rate of evaporation. It leads to decrease the rate of decrease the rate of evaporation, right? Because number of particles will going to decrease on the surface, so the rate of evaporation will going to decrease, na? If it is rate of evaporation going to decrease, so the number of particle or vapors present on the air will also get decreased, which leads to again due to which the pressure exerted by vapors on the surface of liquid of liquid decreases, right? If the pressure is decreased, that means it is called as lowering of vapor pressure. It is called as what? Lowering of vapor pressure. Lowering of vapor pressure. Understood, everyone? Do reply.
Yes,
Yes,
sir.
everyone. Yes. So we have one formula for the same. We already gone through that. P10 is vapor pressure of pure solvent. Pure solvent, right? Again, someone is in waiting room. Wait. Lock here. Okay. So P10 is vapor pressure of pure solvent, and after addition of or dissolving non-volatile solute, okay, let the pressure is P2 beta P2. Therefore, P2 is what? Vapor pressure of solution. Vapor pressure of solution. Now, how much have decreased? How we have to change? How we have to calculate change in pressure? So in that condition, P10 is greater than P2, right? Is it or not? Is it, everyone? Because that pressure is nothing but the lowered pressure, no? How much it is been decreases or change, now we have to calculate. It is change in pressure, is del P equals to P10, okay, minus P2. Okay, that much pressure is going to decrease. Okay, everyone?
Yes, sir.
Yes. So this is the lowering of vapor pressure. After that, we have relative lowering of vapor pressure. So I want you have to like take a screenshot for the same and repeat it once better, because it is really very important. Huh? Oh, where it is gone? Wait a second. Huh? Where it is gone? Okay, now came. What's wrong with OneNote? I don't know. Again and again, it's like moving away. Yes. Now you can take a screenshot, beta. Now it is coming completely. Everyone take a screenshot. Done beta everyone? Everyone keep replying beta.
Yes, sir.
Yes, sir. Done.
Okay. And repeat it once beta. That lowering of vapor pressure is very, very important. Repeat it once and let me know if it is done. I am here only. You have 2 minutes to repeat it. Done everyone, repetition. Samita, Rituraj, Laukya, Bhanuri, Madhusudan.
Yes, sir.
Okay, any doubt beta here?
Yes, sir.
Any doubt? No, na?
No, sir.
Okay, so let's discuss what is lowering of vapor pressure. No, relative lowering of vapor pressure. This is again part of our colligative property. Huh? So I'm going to discuss here only relative lowering of vapor pressure. Okay. Now, next heading, relative lowering of vapor pressure. Relative lowering of vapor pressure. So I'm writing VP only, VP. Okay. Okay. See, relative lowering of vapor pressure, that's just we had to relate with the vapor pressure of pure solvent beta. That's all, not more than that. Okay. So it is nothing but the ratio of the ratio of what? Lowering of vapor pressure. Lowering of vapor pressure of vapor pressure only, not of ratio of lowering of vapor pressure to the vapor pressure of pure solvent. Pure solvent. Okay, that's all. So we had just formula. It's delta P means change in pressure divided by P10. What is P10? Vapor pressure of pure solvent equals to. Now what is delta P means? It is P10 minus P2, right? Is it everyone? Divide by P10. So this formula is for relative lowering of vapor pressure. Any doubt here? Everyone?
No, sir.
Okay. So now how we have to calculate molar mass
No, sir.
of. Okay, now by using this, how we had to like calculate mathematical what molar mass of solute that we are going to dissolve there. Which one? Non-volatile solute. How we have to calculate that we are going to understand now. Okay. Okay, beta.
Yes, sir.
Okay. So till here, any doubt? No, no.
No, sir.
Okay. Okay. Let's check what is been left in notes. Wait, let me check. Chapter is solution. Lowering of water pressure. Okay. Yeah, here we have relative lowering of vapor pressure. That formula we have derived already. There we have like took P2 and here it is P1. Okay, nothing like more than that. Otherwise, it is the same, right? Is it everyone?
Yes, sir.
Yeah. So see here, the relative lowering of vapor pressure is totally depend on the amount of solute that we are going to dissolve, right? Is it or not? Is it everyone? See, if you will dissolve less solute, so vapor pressure which is going to lower is going to be less, or it is will decrease less. But if you will dissolve more solute, so more particle of the non-volatile solute will acquire space on the surface, due to which again number of particle of the volatile solvent going to decrease on the surface, due to which again more rate of evaporation is going to decrease. So less number of vapor will present inside the container or system, and less vapor pressure is going to cause on the surface of liquid. So it totally depend on the mole fraction of solute only, na? Right, everyone? Is it?
Yes, sir.
Yes, sir.
Yes, yes. So it totally depend on the mole fraction of the solute. That's why we can write lowering or relative lowering of, because it relates with mole like number of moles of solute only. So okay, we can write the decrease in vapor pressure or relative lowering of vapor pressure is equals to the mole fraction of solute. Okay, so now we have this formula, that one. Thus, the relative lowering of vapor pressure is equals to the mole fraction of the solute in the solution. Therefore, relative lowering of vapor pressure is a colligative property. Colligative means it depends on the amount of matter of the solute that we are going to dissolve. Okay, so it is a colligative property. Easy?
Yes, sir.
Okay. Now, how we have to calculate molar mass of the solute from the vapor pressure lowering or lowering of vapor pressure, we have to calculate that. It's again very easy. The part of which we have already discussed. So we have delta P. Wait. We have delta P divided by P10 and which is equals to X2. And we know X2 equals to what? Mole fraction of solute. It is equals to number of mole of solute divided by number of mole of solvent plus number of moles of solute. Right? So now we have to place that value. Okay. But if we are discussing about dilute solution, for dilute solution, number of mole of solute will be very less than number of solvent, right? Number of mole of solvent, is it? Suppose in 1 liter of water, we are going to dissolve only one piece of sugar like this, that one, or salt. So thus it is going to change the concentration much? No, na? Is it everyone? So the number of moles of solute, it is for dilute solution only. I am discussing about for dilute solution. For dilute solution. Okay, number of moles of solute will be very less as compared to number of mole of solvent. Therefore, from here that N2 can be neglected. Therefore, X2 becomes N2 divided by N1. Right, everyone? Do reply. Everyone keep replying, beta.
Yes, sir.
Okay. Now, can we write that X and we know what is N2 beta? This N2, N is means the mole, and mole is what? Mass divided by molar mass. So mass is what? W2 divided by molar mass is capital M2, right? Mass divided by molar mass. Likewise for N1, we can write W1 divided by capital M1, right? So can we put that value over here? So can we write X2 equals to what is N2? N2 is W2 divided by M2 beta. W2 divided by M2 divided by what is N1? N1 is W1 divided by capital M1, right? Now we have to solve that further. So we can write it like X2 equals to W2 divided by capital M2. See, that fraction will go on multiple form here, and denominator will go on numerator, and numerator will come on denominator like this. So we can write M1 divided by W1, or we can write X2 equals to W2 into M1 divided by M2 into W1, and which is nothing but is equals to what? Del P divided by P10. Now we have to calculate molar mass beta, molar mass. So what we'll do? We'll transfer molar mass in this side and all this in other side. So we can write capital M2 equals to. Now we have that portion. We have to take that portion. So M2 equals to W2 into M1 divided by W1 into P10 divided by delta P. So this is the formula in order to calculate molar mass of solute, okay, for lowering of vapor pressure beta. Okay, everyone. See here we have the formula, that one. It is nothing but the delta P. Everyone, I hope you got the point. Yeah, here you can write like where M2 equals to molar mass of solute, molar mass of solute means non-volatile solute. Huh? Then we have W2 equals to mass. Mass is like 1 gram, 2 gram, 5 gram. The amount of matter is nothing but the mass, and which is represented by W beta. So mass of solute. Then we have M1. What is M1? Molar mass of solvent. Then we have W1, mass of solvent. Then we have P10. What is P10? Vapor pressure of pure solute. And delta P is what? Lowering of vapor pressure. Lowering of vapor pressure. So I want everyone had to take a screenshot beta for that. Wait a second. Huh? Everyone, take a screenshot, beta. Take a screenshot. I'm making full screen. Done, everyone.